Alright, I want to start with an idea, actually a theory or principle from the end of section 2.3, which I didn't explicitly write down before we finish 2.3, but we're going to use it a lot. It's a really important idea. We've kind of already been using it, but I actually want to write it down officially. It's the inclusion-exclusion principle, which basically says that if you want to know the size of the union of two sets, so this is the cardinality of A union B, in other words, how many elements are in A union B, then that's going to be equal to the size of A plus the size of B, which at first you might just say, yeah, that should be it, right? A plus B, A union B. But there's one extra piece, and let's see what that is. Alright. Let's see if we can figure out what we need to do to alter this, because right now this isn't necessarily correct. If this is A and this is B, then when I say cardinality of A, that's everything in this set, and then cardinality of B plus the cardinality of B, that's going to be everything in this set. But do you see the problem? The problem is I've double counted that area right there, which is the intersection of A and B. I've counted it twice. I counted it when I got A, and I counted it when I got B again. So what I have to do is I have to account for that by removing an intersection of A and B. So this is the inclusion-exclusion principle. So this right there, that's A intersect B, of course. We know that symbol, and what that means. It's A intersect B right there. So as an example, I could use example 2 from section 2.3. I'll alter it a little bit. Let's say, so this is example 2 from 2.3. Let's say that 65 people went skiing and 40 people went hiking and 13 people did both. Assuming everyone on this trip, whatever trip they were going on, a spring break trip, assuming that everyone did one of these two tasks, so no one sat out and did nothing, assuming that everyone did at least one activity, how many people went on this trip? Now we already know this because we worked out the example from a different point of view last time. But what if we didn't know? And you knew how many people went skiing, and you knew how many people went hiking, and you knew that 13 people did both. Well, the naive kind of thing to do would be to add these three numbers up, right? But really what's going on here is we've got 65 people going skiing, so this is the skiing, with 65 total people in here, and then we've got the people that, and notice I'm not writing the number in there yet, right? Then we've got the 40 people that went hiking over here, but the thing is, 13 people did both, and that's where I need to start, 13, in that intersection. And then of course over here we know that this is 52 then, right? Because 52 plus 13 has to be 65, and whereas 40 over here, so this must be 27 people strictly went hiking. So this is straight from example 2 from section 2.3. Okay, so how do I use this inclusion-exclusion principle though? Once I have this, I can just add all three of these up. Okay, and this, adding these three up, is not the same as what's going on here. What's going on here is it's kind of getting around having to make a picture. Okay, once you have the picture down, you can just add each of these distinct sets up, and that'll give you the 92. It's 92 total, I believe. Yeah. But to use the inclusion-exclusion principle, we would say the union of these sets, the cardinal number of the union of these sets, would be equal to the cardinal number of the first set, so 65, plus the cardinal number of the second set, which is 40, minus that intersection. And that's going to give us that 92. Two different ways of doing it. This is using the principle, and this is using the picture. Okay. Alright, so let's now go to section 2.4. Okay, so this section is called Applications and Survey Analysis. So we're going to be looking at some potential real-life applications to this set theory stuff, and looking at survey analysis. So that just means basically you've given a survey to a group of people, now you've got data and you want to analyze it. And we're going to be using Venn diagrams in this section in particular to analyze data. We're actually in particular going to be looking at data that is splitting these people into three distinct groups, or not distinct groups, but three different groups. You can do more than three for sure, but to draw a Venn diagram of a situation with more than three groups is not recommended. It just gets too hard to draw all the intersections of the different sets. Okay, so let's start with the first example they give in the textbook here on page 71. Okay, so they've got a universal set denoted by a rectangle, and we've got Venn diagram with three different sets, and the sets are people that speak Italian, people that speak English, and people that speak Spanish over here. Okay, so this apparently came from a survey that a tour guide gave, and now we've got the data and we're going to analyze it. So we see a bunch of different numbers inside each of these different little sections of the Venn diagram. So starting from the very middle, we've got a 6 right in the middle. This means, since it's right in the center, it's in the intersection of English, Spanish, and Italian. See, it's in all three of these circles. It's in the English circle, it's in the Spanish, and the Italian circle. So 6 people can speak all three languages. Okay, what about this 31 over here? 31, right there. It's in the intersection of Italian and Spanish. Okay, but how do I write that? 31 people can speak. Now, it will not be correct to say this, can speak Italian and Spanish. I need to be a little bit more specific here. I need to be a little bit more specific because these 6 people over here can speak Italian and Spanish, right? They can also speak English. So what I need to do is I need to say 31 people can speak Italian and Spanish, but not English. That is what sets them apart from being in this most exclusive group here. These 31 people can speak Italian and Spanish, but they're not in this English circle. Okay, that's going to be the theme for each of these spots. So down here I've got this 15 in English and Spanish, so 15 people can speak English and Spanish, but not Which circle are they not in? They're not in the Italian, right, circle. Because if they could do all three, then they would be in here, but they're out here. And then the last one of this kind, those 10 people, can speak, so that's 10, can speak Italian and English, but not Spanish. So we've got the innermost group, the most exclusive group, would be the people who can speak all three. Then you've got the people who can speak these two but not this one, these two but not this one, and these two but not this one. So that's what we've got so far. Now, what about these outermost numbers? 19 people. What is this group? 19 people over here. They're in this group that's in the Italian group, so they can speak Italian. Or they're in the Italian circle, part of the Venn diagram. But they are not in the English circle or the Spanish circle. So they do not speak English or Spanish. So they can only speak Italian. "26 people can speak Spanish." So this is how we interpret each of these spots. But not Italian or English. And then the last spot, 110 people can speak English, but not Italian or Spanish. Okay. Now, there is one group that we didn't explicitly discuss here. That's the group out here that can't speak any of these three languages. Maybe there's someone in this group who speaks French and Russian, but they don't speak any of these languages that we focused on in this Venn diagram, so they'd be out here in the universal set of the people being surveyed that didn't fall into any of these categories that we chose to focus on. But there's no mention of those people out here, so it's assumed that every single person that was surveyed gave back an answer that made them fall into either Italian, English, or Spanish, or some other combination of Italian, English, or Italian, Spanish, etc. All three, maybe. Okay. So, that is how we interpret each of these positions on the Venn diagram. The key thing to keep in mind is that these all mean different things. Each spot is distinct from one another. Now, I could ask a question. I'll squeeze it right here. How many people speak Spanish? According to this Venn diagram. How many people can speak Spanish? Well, we've got these 26 that surely can speak Spanish. That's the only language they speak. But then we've got the 31 who can speak Spanish and Italian, so those 31 people can speak Spanish, plus the 15 people that can speak English and Spanish, and then plus the 6 who can speak all three. So how many people in this whole group can speak Spanish? Well, it's whatever the sum of all these numbers in the Spanish circle is. So, whatever this is, let's see, that's 21, 52, so I think 78, I believe. Okay. Now, the hard part about these problems is going from not having a picture to just all of these data points. All of these different data points that I wrote down. This would be like your raw data that you have. You know asking all these people questions, you can organize them by writing it out and have all these data points in front of you, and then you have to make the Venn diagram. That's the tricky part. Or maybe you don't have all of this data, you just have some of it, and you got to do some logical thinking, and you can use the Venn diagram to help you figure out, for instance, a question like how many people can speak Spanish. Okay. Let's look at the official first example. So this is from the text. Okay. The given Venn diagram contains the number of elements that belong to the three sets A, B, and C. Okay, so we've got a universal set. We've got A, B, and so this is just some arbitrary sets. Okay, so just some arbitrary sets here, not naming them or anything, just A, B, C, and they've given us all the numbers already. Okay, so we've got set A with 26 out here, 5, 1, 8, and then in set B we've got 19 and 10, and then finally set C with that 22 there. Okay. Here are the problems. We want to find the cardinal number of each of these sets that they're about to give us. So let's find the cardinal number of A intersect B intersect C. So we want to find the cardinal number of the intersection of all three sets. That's what this means. The intersection of all three sets, A, B, and C. So what is the cardinal number of the intersection of all three sets? How many elements are in this intersection of all three sets? Well, there's only one element inside of all three sets. That's denoted by that 1 right in the middle. Okay, so this is 1. Cool. Let me pull my notes up here, make sure I think I'm going straight with the... Oh, no, okay, yes. In the text, they only give these first two, but in my lecture notes for this section, I give a few more. For practice. Okay, what is the size of the intersection of A and B? So, let's be careful here. We want to add up everything that's in A and everything that's in B. So the only number that's not going to be written here when I write out my sum, because I'm going to write them as a sum first, meaning this plus this plus this, the only number that's not going to be written is that 22, because that 22 does not live in A or B, right? Oh, I'm sorry, that's an intersection, not a union. Oh, God. Yeah, sorry about that. Intersection. Never mind. Disregard what I just said. Okay, we're looking at the intersection, so the stuff that's in A and B at the same time. So not only will the 22 not be involved because it's in C, but this 8 won't be involved, this 26 won't be involved because those are just in A and not in B. What numbers are in A and B at the same time? Well, the 5 and the 1. The 5 and the 1, right? Okay. And C from the lecture notes, so now this is from notes. This point on is from notes. A intersects C. A intersects C. Okay, well, we want to look at the numbers that are in A and C simultaneously. That's the 1 and the 8. So there are 9 elements in A intersect C. Okay, so I can speed up a little bit. Probably get the picture now. B intersect C is the intersection of these two sets, so that's the 10 plus 1, which is 11. Alright, what about E? The cardinal number of A. so just the cardinal number of A. This is where we're going to add up. This is similar to the question I asked earlier about, this is kind of an analogy for how many people speak Spanish. That was asking how many people are in this one circle in the Venn diagram. That's kind of like what's going on here. How many people are in this one set in this Venn diagram? So we've got to add all these numbers up. The 26, the 5, the 8, and the 1. Adding all of the numbers that appear in A. Adding them all up. Excuse me. Okay, so that's going to be 31, 39, 40. And what about the cardinal number of B? The cardinal number of B, well, we're going to add up all the elements, all the numbers of elements that appear everywhere in B. So that's going to be 19 plus 10 plus 5 plus 1, which is going to be 35. Okay. And then G, the cardinal number of the set C. So looking at C, there are 4 numbers in this C circle here. So I'm going to say 22, that's the stuff that's only in C. Then we've got the 10, the stuff that's in B and C, plus the 8, the stuff that's in A and C, and plus the 1, the stuff that's in A, B, and C. Adding them all up to get the total number of elements that are in C. Okay. Alright. Cool. I want to add another problem. The one that I accidentally was thinking about earlier, A union B. A union B. Well, according to the inclusion-exclusion principle, A union B is supposed to be the sum of the cardinal number of A plus the cardinal number of B minus the cardinal number of the intersection of A union B. So we've already got all of those here, all 3 of these things, and let's see if we just kind of plug in. The cardinal number of A was 40 plus the cardinal number of B, which was 35, minus the intersection, which was 6. Okay, so what is that? 75 minus 6, so that's 69 people in the union of A and B. Now let's see if that checks out with what's going on in the picture here. If I wanted to find A union B, that means everything that's in A plus everything that's in B. So I would say 26 plus 5 plus 1 plus 8, that's everything that's in A, plus 19 plus 10, that's everything that's in B. Well, the 5 and the 1 are also in B, but I already counted them. So I would say 26 plus 5 plus 1 plus 8 plus 19 plus 10. Okay, and what does that give us? Okay, that's 31, that'll be 20, 51, 59, awesome, the same number, 69 people, cool, so it checks out. 2 different ways of doing the same problem. You can, if you have the picture, you can kind of just point at all the numbers that are in A union B, making sure not to double count the 5 or the 1. But when you have the picture, it's pretty easy not to double count it. You just got to make sure you hit every number once, right, that's in A or B. But if you want to use the inclusion-exclusion principle, you can do that as well. It holds up here as well. Good. Okay, let's keep going with example 2, which is from the notes or the text. It's the same. Okay. So we've got a universal set that is the letters of the English alphabet. And I'll just list it in roster notation and put that Z, the dot dot dot, and then the Z. It implies that all the letters of the alphabet are there. Let's let A capital A be set of vowels. Let's let B be the letters A, B, C, through L. So A through L. And then let's let C be the letters that make up the word alumni. Okay. So we have three sets here. I shouldn't say distinct sets. They're not distinct necessarily. Distinct means that they don't have any overlap, that there's no common elements. But these have common elements. In fact, we can see A is a common element in each of these. And then, of course, there's the universal set, which contains all the English alphabet letters. Now, we want to draw a Venn diagram to show the relationship between all of these sets. I'm going to draw a very large Venn diagram, because we're going to have all 26 letters in here. Now that's something to keep in mind here, that in this Venn diagram, you're not going to see any letter written twice. Okay. Here's A. Here's B. I'm intentionally making B a bit larger because I know the answer. So you may want to do that as well, just for organization's sake, so you don't have to redraw. Oh, well, C didn't need to be as big, but whatever it is. Okay. Okay, so we want to fill out these sets. What you're going to want to do is start from the very center. That's the tip. That's how we determine, or that's how we make sure we don't double count any letters. We don't want to say out here in this set A, we don't want to put like the letter E, and then later remember that, oh shoot, E was in this set B, so it's supposed to be over here. Or even worse, pick a letter like let's see, like I, and say, okay, I put I out here, but then say, oh wait, I is in B, and then you write it over here, and then you go, oh dang it, wait, I was in C too, so it's supposed to be in the very middle. Always start from the very middle and work your way out. Start from the most exclusive little club here, right in the center, and then work out here, and then here, and then here, and then to the last spot, out here, here, and here. Okay, to the least exclusive spots. Alright, so what is in the intersection of all three of these sets? The letter A clearly is. We can see A. Okay, so the letter A is in there. I mentioned the letter I. Well, let's see. Let's start with the smallest set here. We can just go letter by letter here. E. Okay, E is in A, E is in B, surely, but it's not in C, so skipping E. I is in all three. It's here, it's surely in here, because that's A through L, and then I is there. And in fact, that's going to be it, because O is not in B or C. U is in C, but it's not in B, so it's not in the intersection of all three. Okay, so there's A and I. Now, what about the intersection of A and B? Well, so looking at these two sets, A is there, but we've already got that A, the little A, written in the middle, so that's done. E is there, right? E is in A, E is in B, but it's not in C. Let me make sure that looks like an E. Okay. I is in A and B, but we've already got it written there in the, because it's in all three, it's already written there in the center. O is not there, and U is not there, because the set B stops at L. Okay, so there's only one letter in the intersection of A and B. What about the intersection of A and C? Well, the A, but we've already got that. No E, no I. Oh yeah, I, but it's already in the very center. Oh, no, but the U is there. And that's the only one. Okay. How about the intersection of B and C, so this area here? So I'm looking at intersections first, looking at the innermost intersection very first, and then working my way out. B and C. A, B, no. L is there. L, U, no, M, no, N, I. Okay, so that's it. Just one letter in B and C. Now, what I do is I write the remaining letters that are in A out here. So let's see. A was all the vowels. So A, E, I, O, and U. So now all of those letters are in the set A. These are organized in different positions. So in A, all the vowels, I have A, E, I, O, U. And O is the only one that's the only letter that is strictly in A and not in any other set. Now for B, I'm going to have, okay, A is taken care of. I've got the B, then I've got C, D, let's see, A, B, C, D, E, okay, that's taken care of. F, G, H, I, but that's already there. J, K, and L, but L is already over there. So lots of stuff that's in B that's not in any other set. Now, what about the stuff that's left in C, the word alumni, or rather the letters that spelled alumni? Well, I've got the A already there, the L already there, the U, okay, not the M or the N, and then the I is already there. There we go. That's these three sets with all these different letters organized, right, into their respective positions. The most exclusive set being, or position rather, being right here in the center of all three sets, in the intersection of all three sets, the A and the I. Okay, then the L in the intersection of B and C, the E in the intersection of A and B, the U in the intersection of A and C, and then the letters that are strictly only have a home in their original set. Now, I said that every English letter would be written once in this Venn diagram, right? So what I have to do now is write all of the English letters that did not get included in any of these sets. So B already takes care of A through L, so I would pick up after L with M and N, but those are already taken care of. So let's see, A, B, C, D, F, G, H, I, J, K, L, M, N, O is taken care of. Then there's P, Q, R, let's see, S is not taken, S, T, U is obviously in there, V, and then W, X, Y, and Z are not in any of these sets. So these 10 letters are letters that were not in any of the sets that we looked at here. They are in our universal set, though, so they deserve to be noted out here. Whoops, out here outside of these three sets. Okay. Okay, last example here is from the notes. Let me get to it. All right, example 3. Okay, a survey of 400 customers at an ice cream shop showed that, and then we have 7 different data points here. I won't make you guys watch me write them all down.